Hey everyone, Nathan here. In this video, I will be giving you my take on section 3.9, which is all about related rates. Related rates, most students find to be one of the two hardest sections in Calculus 1. The reason for that is almost all the problems are word problems. However, once you get past the fact that you have word problems and you can write down some equations, then the math isn't too bad. So in related rates, we're assuming that every single variable out there is a function of time, and we differentiate any equation we get with those variables with respect to time to get. So for example, here we've got this equation x squared plus y squared equals 100. When you differentiate that with respect to time, the derivative of x squared is 2x, but since we're considering x to be a function of time, the chain rule kicks in and we have to multiply by the derivative of x, which is dx dt. And similarly, the derivative of y squared is 2y dy dt, and then the derivative of 100 is 0, because derivative constants are always 0. But you have one equation relating your variables, and then you get another equation relating possibly the variables and their rates. Again, the challenging part of this is the fact that it's word problems. And for whatever reason, students find word problems to be the most challenging, perhaps because you actually have to engage a pretty high level of thinking in order to solve the word problems, much higher level than, say, plugging numbers into a formula, or even applying some differentiation of formula to some function. So the book gives its steps, which are perfectly nice steps, but in my experience, they're not quite adequate to get most students comfortable with related rates. But we'll read the book steps anyway. So first, you read the problem carefully. And basically, it just means you really have to understand the problem. Of course, you can't solve something before you understand what it's asking. And then draw a picture if applicable, and then introduce notation, symbols to all quantities that are functions of time, and then you express the given information and the required rate in terms of derivatives. You find an equation that relates the various quantities to the problem, and then you use the chain rule to differentiate both sides, and you substitute. Sounds pretty easy, but a lot of these steps, the way they set them out, are actually pretty hard to implement. So I've got my own version of how to think about these problems. Okay, for reasons I can't explain, the video stopped working, but it's also late and I've taken too long to get this video to you already, so I'm just going to continue on, and I apologize for it. So, as I was saying, in the PDF I have for my take on section 3.9, I put the steps that I suggest you follow in blue. And then everything else on this PDF is how you apply those steps to solve an actual problem. So, we're going to consider the following problem. A man starts walking north at 4 feet per second from a point P. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of P. At what rate are the people moving apart 15 minutes after the woman starts walking? So how are we going to solve this problem? Well, step one is you're going to read the question carefully. You're going to make sure that you understand everything that's going on in the question. And then you're going to write down the answers to the following questions. First, what exactly is the question asking you to find? Secondly, what are the specific facts you're given? Next, some of the things happening in the problem are happening for all time, and you're usually asked to find something that's happening at an instant in time. And students often confuse those things, but be really careful. If something's happening at an instant in time, it can still be a variable, even though the problem might give a value for it. And you should also think about, what are all the rates being given? Or what are the rates that the problem is asking you to find? If you can put all these facts in front of you, doing the rest of the problem will be a lot easier. So back to the problem. First, what are we trying to find? Well, the last sentence says, at what rate are the people moving apart 15 minutes after the woman starts walking? Therefore, we are trying to find the rate at which the people are moving apart at the instant in time 15 minutes after the woman starts walking. In fact, I have a bad feeling that I've done the question for after the man starts walking, but we'll just deal with that later. Next up, what are the individual facts we are given? Well, one fact is that the man is walking north at 4 feet per second from a point P. Another fact is that the woman is walking 5 feet per second south at a point 500 feet due east of P. Next up, what is happening for all time and what is happening at an instant in time? Well, for all time, the man is walking north and the woman is walking south, or at least she's walking south 5 minutes after the man starts walking. So those are kind of universal things that are happening for all time, or at least all time into the future. And what's happening in an instant in time? Well, the only thing that's happening in the instant in time is that's the instant we want to find the rate at which the people are moving. So it's 15 minutes after, and I believe I'm going to solve this problem for when the man starts walking. And then what rates are given and what rates are being asked about? Well, one of the rates is the rate at which the man is moving. Another rate is the rate at which the woman is moving. And lastly, we're being asked about the rate at which the people are moving apart at some instant in time. Now for our next step, we need to ask, which of the quantities from the previous step are varying? Almost all of the quantities that are varying will need to be assigned variables. In fact, that's why the word variable is what it is. It is allowed to vary. However, the rates given, those aren't going to be variables. Those have to be derivatives with respect to time of some of your variables. So any rate given is going to have to correspond to a derivative of a variable. Thinking about this can help you figure out what your variables need to be. So for our problem, what is varying is the position of the man and the position of the woman. And you can represent the position of the man as a variable in several different ways. For example, you could think of the man as walking in the plane and then have x and y give the x and y coordinate of the man. However, this isn't going to be the best choice since the man's x-coordinate is not changing. So instead, we're going to assign the variable m to denote the distance the man is from the point P, just at some arbitrary moment in time. And we're going to let w denote the distance the woman is from the point 500 feet due east of P. Since we are asked to find the rate at which the distance between the man and woman is changing, we're also going to need a variable for that distance. I'm going to call it capital D. I would call it lowercase d, but then it gets quite confusing when you have all your ddt's. You would have d dt with a lowercase d would look really funny, so I'm going with capital D instead. Now, every single one of our variables has to be a function of time. So you can kind of do a sanity check here and think, are these actually functions of time? And if any of them don't change with respect to time, then you have chosen the wrong variables. Now for the next step, you need to write down one or more relations between your variables, and these relations are usually indicated somewhere in the problem. When applicable, drawing a picture of the problem can definitely help. So I just sketched out the following picture. You've got this point P. The man has walked north from P. You've got this point 500 feet due east of P, and the woman has walked south of P. So this distance m is the distance between the man and P. This variable w is the distance from that other point and wherever the woman is. So how can I get a relation or an equation between these variables? Well, I can observe that now I've got everything in this big right triangle. Let me trace it out again for you. It's a big right triangle. One side of the triangle is m plus w. Another side of the triangle, it's down here, but since it's part of a rectangle, it's the same distance as here, which is 500. And now the capital D is the distance between the man and the woman, and that is now the hypotenuse of the right triangle. So from the Pythagorean theorem, we get the relation that the quantity of m plus w squared plus 500 squared is equal to d squared. Now the next step is to differentiate relations with respect to time. This will give new relations, aka new equations, between some of your variables and the rates that are involved in your problem. You don't always have to differentiate every relation, but you always have to differentiate a relation which involves the variable whose rate you are trying to find. Now in our example, we only had one relation, though in more complicated examples you'll have more. However, since the variable we're trying to find the rate of is capital D, we're definitely going to you'd have to differentiate some equation that had a capital D in it. So we're just going to differentiate the one equation we have, and by the chain rule, we get the derivative of the left-hand side is 2 times the quantity of m plus w times the derivative of m plus w, which is just dm dt plus dw dt. Of course, the derivative of 500 squared is a constant, so it's 0, and now the derivative of d squared is 2d dt dt. And therefore, we've got an equation with the related rates. Now, at this point, you want to use that extra bit of information given in the problem that relates to some instant in time. So there's some instant in time that you're going to want to be able to find the values for the various variables at that instant, find the values for their rates at that instant, and hopefully you'll have enough information to then solve for what you're trying to find. In our example, we're trying to find d dt. That means we're going to have to know capital D, we're going to have to know dm dt and dw dt, and we're going to have to know m plus w. But we're trying to find it at the instant in time, which is 15 minutes after the man starts walking. And again, I apologize here. The problem said after the woman stops walking, but I've already done this for the man, so we're just going to change the problem. So since the man is moving at 4 feet per second, after 15 minutes, the man has gone 4 times the number of minutes, which is 15 times 60, which is equal to 3,600. So that's the distance the man is from the point he started out after 15 minutes in feet. And the woman is moving at 5 feet per second, but she started 5 minutes after the man. So that means she'll only have traveled for 10 minutes at that moment in time. So her distance is therefore 5, her rate, times 10 times 60, which is 3,000. The problem just straight up gives us that the man is moving 4 feet per second, so dm dt is 4. And it gives us the woman is moving at 5 feet per second, so dw dt is 5. Now, this has accounted for every single one of these variables on the left-hand side, but we still have to account for capital D. How can we find capital D at the instant? Well, we go back to our original relation. Our original relation had that the quantity of m plus w squared plus 500 squared equals d squared. So now we can plug in our values for m plus w at the instant in time, 15 minutes after the man starts walking. So earlier we found that the m was 3,600 at that point, the w was 3,000 at that point. So we get the equation 3,600 plus 3,000 quantity squared plus 500 squared is equal to d squared. And if you solve that for d, we'll then get 6,618.9 approximately. And now we can plug everything into our relation with the rates. And we'll get this lovely equation here. So 2 times the quantity of 3,600 plus 3,000 times 4 plus 9 equals 2 times 6,618.9 times d dt. And then we just solve that for d dt. Again, I'm sorry about this typo. This should be a d dt, but d dt is now going to equal the 8.9743 feet per second.